We're going to look at the data from the activating strategy in a little bit more detail. So from the histogram and the box plot in the warm-up, you'll see that this is actually the numbers that came out of it. And remember that these are in thousands of dollars, so this would be like $2.1011 thousand. So sometimes they use decimals to make the numbers not so large, so they're easier to deal with. So in the warm-up, it said something about figuring out if something was an outlier by using this idea of 1.5 times the interquartile range. So the idea is that here's your interquartile range, and you want 1.5 times bigger than that, and anything bigger than that would be an outlier, or 1.5 times smaller, and anything smaller than that would be an outlier. So a good visual would look something like this, where you have your interquartile range and then 1.5 times bigger. So we can see that there's something here that's a little bit larger than that, or 1.5 times smaller. We don't have anything over here, so we don't have a small outlier, but it looks like we do have a larger outlier. And if you see, I actually calculated it to help me count by saying, okay, my interquartile range was my difference between my Q3 and my Q1. So 5 minus 2 is about 3. And then that 1.5 times bigger than that, multiply it by 1.5, is 4.5. So if I count from my Q3, 4.5 spaces away, I end up somewhere around here. So I do have an outlier. I'd have to guess what it is just based on this information. But I do have now a way to see the data. So we have all of our data displayed here, and it wants us to use technology to find the mean absolute deviation, and the 5-number summary, which are those numbers that you need in the box and whisker plot. You can see on the screen over here, I've already used Desmos to calculate all these values, and I'm going to make another video that goes into detail about what all of this means, so you can watch that video. But for now, I've just had my data set. I called it Z in here. I found the mean absolute deviation, the first and third quartile, the median, and then the minimum and maximum I actually see in the data set because they're listed in order, so my smallest and largest numbers. So I'm just going to take and record that data here that's on the screen on my paper. So we have our data recorded here, and the next question says the maximum value in the data set actually does represent the United States spending, and we want to know if that number could be considered an outlier. So that number was 9.8923, and we want to know if that number is actually an outlier. So we're going to use this idea of 1.5 times larger than the interquartile range to decide if it is an outlier. So first, we need to determine the interquartile range. So our interquartile range here is going to be our Q3 minus our Q1. So I'm going to take 4.8398 and subtract 2.1495 to find that difference, to find my interquartile range, and that number is 2.6903. Notice I rounded all of my numbers 4 spaces past the decimal because my data set had that as well. Okay, so now I have the interquartile range. Now, this is all I've found right now is the actual distance here. Remember, we estimated it to be 3 earlier, but now we have our exact values, so I estimated that to be that number. Now I want 1.5 times larger than that. So I want that number times 1.5 so I can figure out where that number is. So I need to multiply this by 1.5. So I take my interquartile range and multiply it by 1.5. And when I do that, I get 4.0355. So this number right here is my interquartile range, and I multiplied it by 1.5, and this is the result that I got. So this is how far I want to count away from my Q3. So I want to count 4.0355 numbers away from Q3, and I want to count away from Q1. But notice there's not going to be anything past Q1, so I don't have to worry about that. But if your box and whisker plot had gone that far, you'd want to do both sides. So I only have to do this side because I only have an outlier on that side. So what I'm going to do is I'm going to take my Q3, take that number, and I want to add what I just found, that 4.0355. So I want to take Q3 and add that to it so I can figure out where I end up. So when I add Q3, which we found up here, and that number together, I get 8.8753. And so now anything that is bigger than this number is considered an outlier. So let's look back at our number we're trying to compare, and we'd see that 9.8 is bigger than 8.8 if we think about it a little more easily. So this number in our data set is bigger than the require amount right here. So therefore, it is definitely an outlier. Although outliers shouldn't be removed without considering why they're an outlier in the data set, sometimes it's important to remove it to see how much it's actually influencing the data. So what we're going to do is we're going to remove this outlier in our calculations on the Desmos calculator, and we're going to see how that affects all of our information. All the way over to that maximum outlier, and I'm going to delete it. All the new values are recorded when I took out the outlier, that large outlier, to see what happened and how they were affected from my previous data. So if I go back to my original data, so over here is my original, we can see that the mean, the average actually went down when I took the outlier out. The mean absolute deviation went down a little bit when I took the outlier out. The minimum stayed the same because that smallest number in my data set isn't changing. The quartile 1 went down just a little bit. The median went down a little bit. Quartile 3 went down a little bit. And now our maximum is different because we took out that large maximum number. So the next number in line is now our maximum. So you can see what happens is when we take out that large outlier, everything went down, because think about this number is a big outlier. So when we take it out, all of our numbers are now a little bit closer together and they're all a little bit smaller. So we expect all of our averages and all of our measures of spread to be a little bit smaller.